Here's a good challenging problem on topic 3 for IB physics. We've got 5 kilograms of a hydrogen gas. That's mass. And it's hydrogen-3 gas, so that's the molar mass in grams per mole. It's held in a container of volume 0.700 meters cubed. That's volume, capital V. The gas is heated by a heater with constant power from a temperature of 600 Kelvin, that's initial T, to a temperature of 700 Kelvin. And how long does that heating take? It takes a time of 255 seconds. The density of the gas, that's rho, is 89.88 grams per meter cubed. Okay, calculate the gas's internal energy and initial internal energy and final internal energy. Well, I've got my list, my givens listed. Internal energy, I know that's U. So I'm looking for U, but do I have any equations in my booklet that have U? Let's see. Well, this is topic 3. That's heat energy. That's kind of like U, maybe. And then I've got kinetic energy. That's another form of energy. But which one of these is going to be useful to me? I know delta T. I know mass. But I'm not given the specific heat of the gas. So I can't use this to figure out how much the internal energy rises. Okay then, let's see, what about this? Kinetic energy. What's that have to do with internal energy? Oh, well, wait a second. Internal energy is just the sum of all kinetic energy for all the particles, plus the sum of all potential energy for all the particles. Now, we don't know anything about potential energy. This is a hot gas. Oh, I'm supposed to assume that there is no potential energy because it's an ideal gas. So let's assume it's an ideal gas. That's the only way to do anything on this question. Assume ideal gas. We've got high temperature. That's good. That's a reasonable size volume, so it's probably low density. We can make this assumption. So if I want the total kinetic energy, I'll use that formula. 3/2 times Boltzmann's constant times the temperature, right? And Boltzmann's constant, that's something we're given. Here it is, Kb. If we go up to the fundamental constants, it is the, what is this, 5th one down, and it's 1.38 times 10 to the minus 23. But that's the, let's go back to the equation booklet, because there's a bar over the Ke, the Ek. See that bar right there? That means average. This is the formula for one molecule's kinetic energy on average. So if you have a bunch of molecules all whizzing around, then you need to take the average amount and multiply by how many molecules you have. We are ready to solve. We know 3/2, we know K, we know T. Wait, but we don't know N yet. So let's go find N. What equation does N appear within? Well, there's only one. It's this one. So I know Avogadro's number. If I'm going to find big N, I need to find little n first. How do I get that? I have mass and molar mass. So I use the equation for molar mass. I plug in my 3.00 grams per mole. The mass of my substance, how much I actually have, is 5 kilograms. So kilo is 10 to the 3. I'll put that into the same units, so grams cancel. Grams do cancel. And N comes to, oh, we don't need a calculator for this. 5/3, that's 1.66 repeating. That's how many moles there are. Now that I know N, the number of moles, and I know Na, Avogadro's number, I can find big N, the number of molecules, or particles. So I plug in my, let's go down, I plug in my 1.666 repeating 7 times 10 to the 3. Avogadro's number, we look in our data booklet. Look on the page with the fundamental constants. Here it is, 6.02 times 10 to the minus 23. I'm dropping off the units, but they do work. I cross multiply to get the value of n. Oops, positive. What am I doing? And this comes to 10. Oh, sorry. We'll do 1.003 times 10 to the 27. That's how many molecules we have. And now that I know this value, I have all of the givens necessary to calculate the initial internal energy. So I do exactly that. Three halves. Boltzmann's constant, that was 1.38. We can look back again. Times 10 to the minus 23. And the temperature initially was 600 Kelvin. And this comes to a lot of joules. But we could write that if we wanted. I could take one of these powers of 10 and multiply by the 1.25. And now I would have 6 powers of 10 remaining. And 10 to the 6 is mega. So megajoules. I do the same thing for the final internal energy. I just, instead of using the initial temperature, I use the final, which is 700 Kelvin. And what do we get? 14.5 megajoules. And I'm rounding here. Okay. Part B. State an assumption that's being made. Oh, look at this. We already wrote it down, didn't we? Did we write it down? We're assuming that we're working with an ideal gas. So that is our assumption. We were not told it's an ideal gas. We have to assume it to do anything with this question. We're assuming the hydrogen gas acts as an ideal gas. Next part says, determine the specific heat capacity of the gas. That's C. But C... what equation does C appear in? Well, it only appears in this equation. So I know the mass of the substance. I know how much the temperature changes, 100 Kelvin. And I'm looking for this, but do I know how much heat is added to the substance? Well, wait a second. You've got this gas in a box. And the molecules are in there. And you're adding heat from the heater to heat it up, warm it up, and the internal energy rises as a result. You know, the amount of energy you have U is going up. So the amount that the U changes, the amount of increase, is simply equal to the heat that is added from the heater, the flame, whatever it may be. So I do know Q. It is simply the difference between my two U values. So when I take the difference between, when I find how much the internal energy rose, and I don't round, I get this. The mass, I know, I need to use that in kilograms, because joules uses kilograms too. So the mass was 5 times C. How much does the temperature rise? Well, we do final minus initial, and that's 100. So C comes out to about 4150 joules per kilogram per Kelvin. I should be using the -1 notation, but I'm kind of out of space there. Next question. Calculate the change in pressure of the gas. Now, you might look at this and think we need delta P, which is true, but we don't have delta P in any equation. The only equations with pressure are the definition, force per unit area that's in contact, and the equation of state of an ideal gas. We have no information about force or area, so this is not a useful equation. Instead, we have to use PV equals nRT. We know the volume initially. We know the number of moles. Hey, we know the ideal gas constant, and we know temperature, so we can easily find the initial pressure. We simply use the equation. This stays the same, and N stays the same, but the temperature changes from some initial value to some final. So I plug in, it's 0.700 meters cubed. Check your units. 1.666 repeating times 10 to the 3 moles. R, we look up in our data booklet, it's 8.31, and the initial temperature was 600 Kelvin. And then we're going to do the same calculation for the final pressure. The only difference between the two is the temperature is not 600, we use the final temperature, 700. You get the values of PI and PF, calculate those, then you do final minus initial, and what's the answer that we get? We get, rounded for 3 sig figs, it's 1.98 times 10 to the 36 pascals. Now, if you look to the calculations you got for initial and final, like the initial pressure was 1.19 times 10 to the, let me write it this way. It's 100,345. It's 119 times 10 to the 5 pascals, which is really high. Atmospheric pressure is 1 times 10 to the 5 pascals. So this is too high. The assumption that that we're dealing with an ideal gas is not correct when your pressure is this high. Why? Because this is not going to qualify as low pressure, which is one of the things we need for a real gas to behave ideal. To behave ideal, pressure must be low. That's not the case. So whoever wrote this problem didn't plan ahead. That would be me. Okay, so moving on. Determine the power of the heater. The only equation with power, capital P, is Q over delta T, or maybe energy over delta T. In fact, if the Q, if that's causing the internal energy to rise, we could even do the change in internal energy. That is how much heat, Q, you add. So which one makes sense for us? Well, we are given the time, if you look back, and we know Q, which is also equal to delta U. So we can easily calculate pressure. We simply plug in the time that we were given from before. Let's look back. The time was 255 seconds, and the delta U that we got was the difference between these two. So we plug in those values, 225 seconds. And the delta U was 2.08 times 10 to the 36. And what do we get for power? Well, when I fix this, so that I actually have the correct number of, so that this is the 5, the correct power we acquire is 8.145 watts, which we could round to 8.15 kilowatts. Finally, part F. There's another container with helium-4 at the same temperature. Explain which of the gases, the hydrogen or helium, has a higher average molecular speed. If they're at the same temperature, then they have the same average kinetic energy. If helium-4 has a higher this, then it must have a lower average speed to come to the same value on the left.